In this video, we're going to explore the relationship between strong and weak acids and bases. We'll learn what a strong acid or base is and what a weak acid or base is. So a strong acid is one that completely dissociates into ions when it's added to water. So this would be the example. We have our strong acid before dissociation, and then after dissociation, it's all broken apart into hydrogen ions and the anion. So in this, we'll learn about equilibrium in our next course in chemistry, but basically it all breaks down into those two ions and it remains to the right. So this reaction is complete. So some examples of strong acids would be hydrochloric acid and sulfuric acid. In a weak acid, it doesn't dissociate into ions well at all. So you start with your weak acid. It'll partially dissociate, but you still have some of the acid left and then just some protons and some anions. And then this reaction is going to go back and forth. So some of it will dissociate, but then it'll reform back to the acid and it'll just go back and forth like this. So it's not dissociating ions well at all. So some examples would be acetic acid or citric acid. These are two edible acids, so they're weak. They're not going to be ultra corrosive because not all of them are going to dissociate into these ions. This is what gives our acid its strong properties, this hydrogen ion, and we'll talk a little bit more about that when we talk about pH. So this is an example of a strong versus a weak acid. So we have 1 mole per liter of hydrochloric acid, so it's the same concentration as acetic acid. This one dissociates into ions completely because it's a strong acid, so it's able to light the light bulb up quite a bit, whereas this weak acid, even though it's the same concentration, is not lighting the bulb up well at all. So vinegar isn't as great a choice for an electrolyte in a battery as something a little bit stronger, so a stronger acid. The same thing goes for strong bases and weak bases. So strong bases would completely dissociate into ions. So all oxides and hydroxides of alkali metals will be strong bases, so sodium oxide, sodium hydroxide, etc. Weak bases don't dissociate into ions well at all. And again, you'll see that these are commonly used bases in the home. So sodium bicarbonate, we use it in baking, and then ammonia we can use in cleaning supplies. It is a bit dangerous for other purposes, but it isn't as strong a base as, say, sodium hydroxide. So one thing you should know is the relationship between conjugate acid-base pairs. So a strong acid, like sulfuric acid, would have a weak conjugate base. And a weak acid, so water is very weak, would have a strong conjugate base. So each of these, and like something in the middle, would have about the middle of the road conjugate base. So that is something that you should know, is that strong acids have weak conjugate bases, weak acids would have strong conjugate bases, and vice versa. So we'll talk about water and whether it's acidic or basic. So all solutions contain ions, even pure water. So in even pure water, some water molecules will dissociate into ions. So if you react 2 water molecules together, you'll end up with 1 hydronium ion and 1 hydroxide ion. So in pure water, the concentration of hydronium or hydrogen ions is 1.0 times 10 to the negative 7 moles per liter. Also, the concentration of hydroxide ions in pure water is the same. So the concentration is exactly the same. We're going to see how that applies to pH and what pH means now. So if you look at pH, and remember that hydronium and hydroxide or hydrogen ions are interchangeable, when the pH is 7, the concentration of hydroxide and hydrogen ions is equal. So the pH is 7. If you have an acidic solution, you have more hydrogen ions than hydroxide ions, so the pH is less than 7, and that will make litmus paper turn red. In an alkali or basic solution, you have the pH is higher than 7, and the litmus paper turns blue, and the hydroxide concentration is higher than the hydrogen concentration. Again, if we look at the pH scale, this image from Cognity, it runs from 0 to 14. Increasing hydroxide ion concentration goes to the right. So pH 14, you have more hydroxide than hydrogen ions. Over here, increasing hydrogen ion concentration makes something more acidic. Right in the middle at 7, you have equal concentration of hydroxide and hydrogen ions. So we can use that concentration of hydrogen to figure out our pH of a substance. So the concentration of hydrogen ions can range from 10 moles per liter to 10 to the negative 14 moles per liter. Since this range is awkward, because every change is like a 10-fold change, we use the pH scale instead to indicate acid strength. So we calculate pH as the negative log of the concentration of hydrogen ions. And 1 unit change in pH is equal to a 10-fold change in the concentration of the acid or base. So in this example, we're being asked to find the pH of pure water. So remember, the pH is equal to the negative log of the concentration of hydrogen ions. So that's equal to negative log 1.0 times 10 to the minus 7 moles per liter, and we're going to get a value of 7. So our pH is 7. You can also find the concentration of hydrogen from the pH. So that's equal to, the concentration is equal to 10 to the negative pH. So in this example, we're being asked to find the concentration of solution of hydrochloric acid with a pH of 5.30. So remember, the concentration of hydrogen is equal to 10 to the negative pH. So that's equal to 10 to the negative 5.30. So that's equal to 5.01 times 10 to the negative 6 moles per liter. We can also find POH the same way, so it'd just be negative log the concentration of hydroxide ions. So for example, the hydroxide ion concentration in the solution is 1.0 times 10 to the negative 10. Calculate the POH. So POH is equal to negative log of the concentration of OH, so 1.0 times 10 to the negative 10. So that's equal to 10. So the pH is 10. You can also, if you know the pH of the substance, so that was the POH. If you know the pH, you can just find the POH by subtracting from the pH. So an indicator is something that will tell us if a solution is acidic or basic. And there's different kinds of indicators we'll discuss. It's usually a weak monoprotic acid, so the acid will be one color and the conjugate base will be another. So for example, phenolphthalein, which is one that we use, it dissociates in base to become pink, but it doesn't dissociate in acid, so it remains colorless. So we can use that to identify when a titration has reached its end point. We also use litmus paper. So litmus paper is, it turns blue litmus paper turns red in acid, and red litmus paper turns blue in base. There's one way to remember this. There was a saying in an old video when I was a student where the person would enthusiastically say blue to red, acid, and that always reminded me that red makes acids and blue, B for base, blue for base. So universal indicator is kind of fun. We sometimes use universal indicator paper, and then you can actually find out the pH range of something. So it actually has a series of indicators built in that change color at different pHs. So pH 1 would be red, and then it goes through the whole rainbow of colors all the way up to purple. So blues and purples tend to be bases, and reds and yellows tend to be acids, and then in the middle range is the greens and the teals. So those are more middle of the range. Finally, we can use pH meters to determine the pH of a substance. It's a much more accurate method of determining the pH if you have it calibrated properly. So we calibrate our pH meters with buffers of known pH to ensure that the pH meter is reading the values correctly of our solutions. We will use these in some of our acid-base titrations where we'll measure the pH over time as we add our acid to our base or our base to our acid.